Hello and welcome to Honors Function. In this third lecture on sequences and series, we're going to continue looking closely at a type of sequences called geometric sequence. This lecture will follow the same pattern as the previous one when we looked at arithmetic sequence. That is, first we'll give the recursive definition. Second, two properties. First property will be the explicit formula for a geometric sequence, and the second property will be the formula for the sum of the first n terms. Let's begin. So what is a geometric sequence? So the recursive definition is very simple. You'll be given one term, and then the rule to go from one term to the next is to multiply by a constant ratio. This is called the common ratio. So for an arithmetic sequence, you add the same constant. For a geometric sequence, you multiply by the same constant. That is the recursive definition. Let's go over the first example. Here we go. Let's write the first 5 terms of the geometric sequences. So here in the first one, the first term is -3. And then what is the common ratio? The common ratio is 2. So you multiply by 2. -3 goes to -6, -12, -24, -48, -96, etc., etc., etc. Very, very simple. Please do the second examples. Example number 3. Alright, here I'm telling you this is a geometric sequence. I'm asking you to find the common ratio and the 9th term of the sequence. Okay, so how will you find the common ratio? What's going on between two consecutive terms? You multiply by the ratio. So A2 equals A1 times R. A2 is -5/3. -5/3 equals A1, which is 5/2 times R. Therefore, R is, so you solve this equation for R and you would find -2/3. Alright, so R is -2/3. We have our ratio. Now, I want you to find the 9th term. Which one is the last one I'm giving you? 1, 2, 3, 4. So I'm giving you A4. Now, what happens to A4 if you multiply by R? You would find A5. Multiply by R again, you would find A6. Now, instead of writing times R, I'm going to write R squared. That's A6. Multiply by R again. That's A7. This is, oh, I've lost track. Sorry. So this is A5, A6, A7, A8, A9. Here we go. I need to multiply by R 5 times. I need to multiply by R to the 5th. This is A9. So what is A9? It is -20/27 times -2/3 to the power of 5. So this is going to be a negative, which will make a positive in the product. So we have 20/27 times 32/243. And that is, so of course here use a calculator, you would find 640 divided by 6,561. Okay? All right. You do the next example. This is not much more difficult. Please remember the investment model also for that. That would help you. It's exactly the same thing as it was for an investment model. Okay, let's continue. So now we're going to derive the explicit formula for a geometric sequence. It's not difficult. Check it out. So you're given A1, and then from A1 you go to A2 by multiplying A1 by R. And then if you multiply A2 by R, you would find A3. But that is just A1 times R, right? Times R. That's A2 right here. So it is A1 times R squared. This should ring a bell. We've done the same kind of derivation when we looked at investment model. So AN equals A1 times R to the n minus 1. Okay, here there's one R between A1 and A2. Then there's R times R between A1 and A3, so R squared right here. Okay, and so you would have R times R to the power of n minus 1. All right, so there is another formula. This is the explicit formula when you're given A1 and R. You can also use another formula which is very easy to derive. It's when you don't start at A1 but you start at AK. So how many times do you need to multiply by R? N minus K. Okay, so this is the second explicit formula for a geometric sequence. Let's go over some examples. So in this example, I'm telling you the first term of the sequence is 2, and the seventh term is 128 divided by 729. So A1 equals 2, and A7 equals 128 divided by 729. And I'm asking you to write the recursive formula for the sequence. I'm also asking you to give the percent of decrease between two successive terms. Okay? All right, so how are we going to find the recursive formula? Well, I know A1, I need R. Now, A7 equals A1 times R to the power of 6, 7 minus 1, right? So we have 128 divided by 729 equals A1, so 2 times R to the power of 6. So if you divide both sides by 2, you would find 64 over 729 equals R6. Now, 64 is 2 to the 6, and 729, it's 243 times 3, so it's 3 to the 6. So it is 2/3, okay? This is 2 over 3 power 6. So R is 2/3. Therefore, the recursive formula for the sequence is A1 equals 2, AN plus 1 equals AN times 2/3. Here we go. Let's go over the second question. By what percent do you decrease when you go from AN to AN plus 1? So the percent of decrease, now AN gets multiplied by 2/3, so it is getting smaller. That's why it's a percent of decrease. I will put the absolute value because I don't want to have a negative percent. Okay, that's why I will put the absolute value. So it is AN plus 1 minus AN over AN. That's how you find a percent of decrease. We have seen this formula before. You remember y2 minus y1 over y1. That is the percent of increase or decrease between y2 and y1. We've also used the formula when we looked at some approximation. All right, approximation minus exact divided by exact. That's the same formula. It's a percent of increase and decrease. Okay. All right, let's go over it. So it is 2/3 times AN minus AN over AN, absolute value. Now, factor AN at the numerator, and you have 2/3 minus 1 times AN over AN. Simplify by AN, and it is the absolute value of 2/3 minus 1, so basically it is 1/3. So it is, what's the percent of decrease? It is about, I guess, 33% of decrease between two consecutive terms. Okay, so if you multiply, and this is what it says, right? It says that AN plus 1 is 66%, right? That's 66% right here, right? About. It's 66% of AN. Therefore, the percent of decrease is 33% decrease. Okay? All right, let's go over the next example. So in this example, I'm asking you to give me the term number. Okay, so I mean first term, second term, third term, k term. Okay, I want the term number, so I want k. I want k, not the value of the term. I just want the term number, okay? Of the earliest term when the sequence 1, 1.5, 2.25 exceeds 50. So what kind of sequence is this? Well, this is a geometric sequence. The first term is 1, and the ratio is, what do you do to go from 1 to 1.5? You multiply by 1.5. You multiply by 3/2. And then right here, again, you multiply by 3/2. That's 9/4, right? So R equals 3/2, okay? So here, the sequence is going to increase, okay? 1, 1.5, 2.25. If you were to continue, you would find with a calculator 3.375, and then the next one would be 5.0625, etc., etc., etc. The terms are getting bigger. I want to know the first term that will exceed 50. Now, how am I going to do this? Well, that's pretty simple. I want to know an that will be above 50. Okay? An is a1 times r to the power of n minus 1, right? So, what is a1? It is 1. So it is 1 times, and what is r? 3/2 to the power of n minus 1. And I want to know when this is going to be above 50, okay? You know how to solve this inequality. They're pretty simple. You take the log on both sides, and you have n minus 1 times ln of 1.5 above ln of 50. Therefore, we have, actually, let me go right here. So we have n minus 1 above ln of 50 divided by ln of 1.5. I kept my inequality because ln of 1.5 is above 0, right? Because 1.5 is above 1. Therefore, n has to be above ln of 50 divided by ln of 1.5 plus 1. So this is about 9.6 plus 1, so 10.6. So n has to be above or equal, so this is 10.6, right? So it's got to be above or equal to 11. Okay, you got to take the ceiling here, not the floor. If you take the floor, you're not going to be above 50. So it's got to be above 11. Okay? All right. Let's go over the sum of the first n terms of a geometric sequence. So I want to find a formula that gives me the sum of the first n terms of a geometric sequence. We're going to derive this formula. Here's what you need to do right here. This is a sum. In the arithmetic sequence, we rewrote it, but we reversed the order, right? This is not what we're going to do right here. Right here, we're going to rewrite it, but before we rewrite it, we're going to multiply everything by r. So it is r times a1 plus r times a2 plus r times a3 plus r times an minus 1 plus r times an. Okay, why did we do that? Well, check it out. Let me rewrite Sn, a1 plus a2 plus a3 plus an minus 1 plus an, and right below, let me write r times Sn. What is ra1? It's a2, right? So I'm not going to rewrite it below a1. I'm going to move everything one place. So ra1 is a2. ra2 is a3. ra3 is a4, so I'm not going to write it. ran minus 1 is an, and ran is an plus 1. Okay, do you agree? And here we would have an minus 1. Now, what are we going to do? We are going to subtract side by side. I'm going to do this minus this. Okay, so what do I have on the left? Well, I have Sn minus r times Sn. What do I have on the right? I have all of that minus all of that. Now, this minus sign will distribute, and you see all of these are going to get cancelled, right? They're all gonna get cancelled, and you'll be left with a1 minus an plus 1. Wow, that is very interesting. Factor Sn, so you have 1 minus r times Sn equals a1 minus an plus 1. And so you have Sn equals a1 minus an plus 1 divided by 1 minus r. This is a fine formula, but actually we usually go further. An plus 1 equals a1 times r to the power of, so n plus 1 minus 1. N plus 1 minus 1 is just n right here. So we go a little bit further and we say this is a1 minus a1 times r to the n over 1 minus r. And now if you factor a1 at the top, you land on the formula that you ought to remember. Sn equals a1 times 1 minus r to the n over 1 minus r. Okay? This is the sum of the first n terms of an arithmetic sequence. Let's go over some examples now. Here I'm adding terms of a geometric sequence. To go from one term to the next, what do? I multiply by 1/3. So a1 equals 1/3, r equals 1/3. All right. Now I want to apply the formula. I just don't know how many terms I'm adding here. So this is an, but what is an? An is 1 over 729, but it's also 1/3 a1 times 1/3 to the power of n minus 1. Now 1/3 times 1/3 to the power of n minus 1 is 1/3 to the power of n right here. And this is equal to 1 over 729. So basically what you want is figure out how many times you have to multiply n by itself to find 729. You take a calculator if you need to, but this is not difficult. N equals 6. So this is just the sum of the first 6 terms. Therefore, S6 is equal to a1 1/3 times 1 minus r to the power of n, right? So r is 1/3, I'm sorry. 1/3 to the 6th power divided by 1 minus 1/3. Okay? So what is that? We could play a little bit with this and simplify by hand a little bit, but let me do it with my calculator. You would find 364 over 729. That's what you find when you add the first 6 terms of this geometric sequence. Let's go over the last example now. So in the last example, I'm adding terms of a geometric sequence, and I want to know how many I must add before the sum exceeds 100. So in this case, it is not the term that I want to be over 100, it is the sum that I want to be over 100. Okay? So this is a geometric sequence. The first term is 50, and the ratio is 60 over 50, which is 6/5. Okay, so if you multiply 60 by 6/5, you would find 72, and if you multiply 72 by 6/5, you would find 86.4. All right, so let's answer the question. Sn equals 50 times 1 minus 6/5 to the power of n, I'm looking for n, right, divided by 1 minus 6/5, and I want this sum to be above or equal to 100. I guess if it exceeds, it's got to be above, okay? Above 100. So we have seen this type of inequality in the previous unit. It is not hard to solve. Let me first divide by 60 both sides. 1 minus 6 over 5 to the power of n divided by negative 1/6, right? Negative 1/6 is above 2. So I need 1 minus 6 over 5 to the power of n to be smaller than negative 1/3, multiplied by negative 1/6. Therefore, I need 6 over 5 to the power of n to be above, so subtract 1, that's negative 4/3, so it is 4/3 right here. And of course right here we ln both sides, and we have n times ln of negative 6/5 is above ln of 4/3. Therefore, we would have, again, ln of negative 6/5, that's above 0 because 6/5 is above 1. N is above ln of 4/3 divided by ln of 6/5. And if you take the calculator, you would find 1.5. Therefore, n is above or equal to 2. And then when you write that, you realize, I really didn't think when I wrote this question, because it's above 100 as soon as you add two terms. Duh, I should have picked a better number here. Well, at least I'm glad this computation is giving evidence to my blindness. Thank you for watching.